So when Karen invited me to speak, I decided this was a great opportunity to look at differential privacy in more distributed settings. It's a topic that very recently has had an uptick in research, and I'd like to share with you some of the things that I've found. So when we think about data analysis, we want to differentiate between two kinds. One is to try to get a statistical understanding of a population as a whole. So this would be, for example, with census data, or analyzing loan data for evidence of systematic discrimination, or even machine learning as we train a classifier to distinguish cancerous cells from healthy brain cells. On the other side, we have the sort of needle in the haystack, which was done, for example, in the Total Information Awareness Program, and it was aimed at finding terrorists. And of course, this is still going on. So differential privacy is for the first kind of analysis, and it's simply the wrong tool for the second kind. So if you want to do the needle in the haystack in a so-called privacy preserving manner, you have to define what you mean by privacy there, and you need to develop new tools. What we are doing is not going to be relevant. Okay. So a statistic is a quantity that's computed for us from a sample. And the intention with the statistic is that it tells us about the population as a whole. So statistics feel private. And one of the reasons they feel private is, well, you could have two data sets that were collected independently from the same population and that might not even intersect. And if they're collected independently from the same population and with the correct methodology, then they should tell us essentially the same things about this population as a whole. This is the whole theory of statistics, and this is why statistics works as a scientific endeavor. So the sense of privacy is derived from this fact. Even if there's just one, sample, maybe you think nobody knows I'm in the sample, or I can claim that I opted out. And in a very strong sense, there's this feeling that the statistic is not about me, it's about the population as a whole. And this intuition is on the right track, but it needs some help. And differential privacy provides this help. And in fact, differential privacy preserved this sort of I could have opted out privacy intuition for every computation, including total population counts and other measurements of a total population. Okay. So how do we abstract the problem? Our driving scenario when we started this work was the US Census analysis. So the data that are collected every 10 years, let's say, by the US Census, huge amounts of data, literally billions, more than 11 billion statistics released about these data with enormous social and political consequences. So we abstract the problem as follows. We have a data analyst, and this is not a trusted party. And the data analyst asks a query. It could be a request for a measurement or a statistic, or it could be for tables or whatever, asks a query from this database and gets an answer. And then adaptively, seeing this answer, chooses a next query, and so on and so forth. And we imagine that we have sort of the database versus the world. So the trust boundary, which is, I'll be using pink dashed lines during the talk, the trust boundary is around the data and maybe a curator, a trusted curator that has access to this data, like the Census Bureau. And the entire world of data analysts that could collude and so on and so forth are abstracted by our single data analyst here, who can be arbitrarily nasty. So we're going to use flossing as a personal question during this talk as an example. You might say, starting with this introduction that I gave, that all that should be released are statistics, assuming that we could capture that intuition of what a statistic is as something that's about the population as a whole. So what about just statistics? Maybe you can only answer queries if the queries are about a sufficiently large number of individuals in the data set. And that immediately doesn't work. So suppose we had the exact answers to these two questions. How many members of the House of Representatives floss regularly? And how many members other than the Speaker floss regularly? If we had the exact answers to both of these questions, even though the House is a pretty large group, we would know whether or not Nancy Pelosi flosses regularly. And that's just this differencing attack is just one example of how sort of seemingly innocuous large statistical queries over large sets can be combined to compromise privacy. More generally, the so-called fundamental law of information recovery, also known as the database reconstruction theorem, says that sort of overly accurate estimates of too many statistics is blatantly non-private and completely destroys privacy. And notice that this doesn't actually get into the details of what was the protocol for getting one's hands on these estimates. So this theorem applies whether we're in the question and answer setting or whether the data curator releases some kind of algorithmic blob that contains the answers to sort of all the possible statistical queries that one might ask or that one might be interested in. So, and the definition of overly accurate is actually tied to the definition of too many. If you want to only ask a small number of statistics, you can answer them with very high accuracy. But if you want to answer to provide many statistics, as in the case of the census data, then overly accurate, you have to degrade the accuracy. And this is the theorem. This is a fundamental law. There's no magic that can make this go away. Okay. So as I said, this is independent of the protocol for getting one's hands on these estimates, and so it applies equally to non-interactive systems. Now, I said the Census Bureau publishes billions and billions of statistics. So this year, for the first time, the Census Bureau will be using differential privacy as the means of disclosure avoidance for the decennial census. And if you're wondering what kinds of harms can come to people as a result of violations of census data privacy, one example is, say, removal from federally subsidized Section 8 housing. So this is housing assistance for which a family may have waited years to get one of these homes. And if there's a violation of the lease agreement, maybe too many people are living there or not immediate family are living there, then they could lose the housing. And this is very, very severe. And the Census Bureau has a legal mandate for privacy. So this is what they're using. And the reason that they decided to do this was precisely that fundamental theorem that I told you about. That is literally the attacks that Dinur and Nissim and others have figured out how to carry out on reconstructing individual responses from large numbers of relatively accurate aggregates. Okay. Now, this was not a smooth ride, and it's not over. And, we're expecting, there was a lawsuit that ended recently. We're expecting many others, so you can ask about that during the question and answer period. Okay. So let's get into the definition of differential privacy. This is a picture of Cecilia Helena Payne Gapushchin, who was among the first women to obtain a PhD in astronomy and the first person to obtain one at Harvard. And she ascertained that the temperatures of the different classes of stars, she ascertained temperatures of different classes of stars and estimated the great abundance of hydrogen in them, much more than in Earth, while doing the research for her dissertation. And this contradicted the belief at that time that the sun and the Earth had similar composition. Now, definitions are essential, and without them, we literally do not know what we're talking about. So what do we mean about privacy preserving data analysis, and what kind of protection should we offer to Cecilia Payne? So ideally, what we'd like is to learn the same things, even if Payne had decided not to join the data set, even if we had omitted her data. Of course, there are limits to what you can do with this kind of ideal, because otherwise we could keep eliminating people and we'd be asserting that what we learn from the database as a whole should be the same as what we learn from an empty database, and then we wouldn't be learning anything and there would be no purpose. So we get around this, or we capture this nuance with the essentially equally likely term in this English language definition of differential privacy. It says that the outcome of any analysis is essentially equally likely, independent of whether any individual joins or refrains from joining the data set. So the same thing when Payne is there, when Payne goes away, if Payne is replaced by Pelosi, and so on. And this resilience to small changes in the data set actually aligns well with generalization in machine learning. So it's known that if your algorithms are not robust to small changes in the data set, then the results will not generalize to the population from which the data set has been drawn. So differential privacy is a very strong notion of privacy, but at the same time, it aligns well with generalization. Okay. And differential privacy allows us to disentangle harms that could come to people from harms that come from the teachings of the database. So for example, learning scientific facts that, that smoking causes cancer, which might cause a smoker's insurance premiums to rise. So disentangling harms that come from the teachings of the data set from harms that arise due to participating. If I'm essentially no more likely to be harmed whether I join or not, maybe I will be persuaded to allow my data to be used for these sorts of purposes, which has a public health benefit. So now we're ready for the mathematical definition of differential privacy. For historical reasons, the algorithms are typically called mechanisms, and so they're named M. And differential privacy is not binary. That is to say, it's true that there are algorithms that are not differentially private, but in the differentially private ones, there's a level of privacy loss or bound on privacy loss. And that's given by a parameter typically called epsilon. And we need one more concept, which is the notion of adjacent data sets. So two data sets, X and Y, are adjacent if one is contained in the other and the larger one has the data of just one more person. So for example, that database and the database without Cecilia Payne. So then we say that a mechanism M gives epsilon differential privacy if for all pairs of adjacent data sets X and Y and all possible output events S, the probability that we see output event S when the mechanism is operating on X is very close to the probability that we see output event S when the mechanism is operating on data set Y. And this very close to is captured by e to the epsilon, which is approximately 1 plus epsilon when epsilon is small. And the roles of X and Y are completely symmetric in this definition, so the other inequality holds as well, with X and Y swapped. And this parameter epsilon is sometimes called the privacy loss bound or the privacy budget. No, actually just the loss bound for the algorithm. And this is also called a bounded ratio condition. If we divide both sides by the probability of seeing S on M of Y, we get that the ratio of probabilities is bounded by e to the epsilon. And the probability space is over the randomness that's introduced by the mechanism M. So M is going to flip coins, and that's good because we control M. M is like one of the good guys. And so it's a worst case definition over all, worst case over all adjacent X and Y. Yeah, good, okay. So notice that this is a statement about the behavior of the mechanism. And this statement doesn't sort of care about who knows what. And this actually holds now and in the future. So differential privacy is sort of future-proof, that even if you knew that an algorithm was operating on either X or Y, and you knew all about X and Y, nothing you can learn in the future will tell you retrospectively which of the two databases was actually in use. So what this says is you can learn things about pain, but you can only learn things that you could have learned without pain. So this is the what we chose to be a sufficient privacy definition. And getting back to the needles and the haystack, differential privacy by definition hides the needle, because these two data sets, X and Y, the haystack versus the haystack without the needle, are adjacent. And when we made this definition, we felt it was extremely important to protect outliers, that outliers are in fact often the ones most in need of protection. Okay. So key properties of differential privacy that flow from the definition. It's future-proof, as we've discussed. It composes gracefully and automatically, so we can understand mathematically the cumulative privacy loss over multiple differentially private computations. And at worst, these losses add up. We'll say a little bit more about that later. So if you have an epsilon, if you run an epsilon1 differentially private algorithm on the database and release the result, and then you run an epsilon2 differentially private algorithm on the same data and release that result, the transcript, the cumulative privacy loss, is bounded by epsilon1 plus epsilon2. And that's a key property because it means that differential privacy is programmable. That is, you can design complex analytical tools that are built from small differentially private building blocks or subroutines. And we can understand through the composition theorem how the privacy loss adds up. And we can also control that by decreasing the parameters for the intermediate steps. So again, this is the sort of heart of the reason differential privacy is so powerful. Okay, so one example in this model is the Laplace mechanism. So this is a mechanism, differentially private mechanism, which takes a database and a parameter epsilon, and it returns a k-dimensional vector, a vector in k-dimensional Euclidean space. Okay. And the Laplace distribution is shown here on the right. So we always have Laplace distribution with mean 0. And it says that sort of the probability of getting far from the mean is falling off exponentially. So the algorithm says if you want to release a k-dimensional vector function of x, you compute f of x, and then, no, did that by itself. And then you sample k times independently from the noise distribution, the Laplace distribution, that has a parameter, the sensitivity of the function divided by the privacy loss. So the sensitivity of the function is a measure of how much the data of any one individual can change the value of the function. It's an upper bound on that. It is a property of the function, not of the database. So the sensitivity is defined here. It's the L1 norm, or if this were one-dimensional space, it would just be the absolute value. And so as you might expect, if you have a high sensitivity function, you're going to need to add more noise to hide the presence or absence of one individual, and that's captured by having the sensitivity in the numerator. Now, if you want better privacy, you also want more noise. You want to stretch things out. Better privacy for us is smaller privacy loss. So good privacy is tiny epsilon. So here's epsilon in the denominator, making sure that when epsilon is small, this privacy, this noise is spread out. And if you do this, then the L infinity error of your answer satisfies this bound, that the probability that your error, infinity error, is more than log of k over delta times this parameter, delta f over epsilon, is bounded by delta. Okay. So for example, suppose we're asking counting queries, which is something we're going to be talking about for the rest of this lecture. How many people in the database like to eat muffins? So the presence or absence of one person can change the answer to that query by at most 1. So the sensitivity is 1, and the dimension of the output is 1. It's just a real number. What about if I asked 50 counting queries, 50 arbitrary counting queries? How many people like to play the violin? How many people like pasta? How many people like pizza? And so on. You know, one person might change the answer to all of those 50 queries. So the number of queries, the dimensionality is 50. You could think of it that way. And the sensitivity is 50. On the other hand, a very important class of queries are histogram queries, where we take the space, whatever the space is, maybe it's incomes, and we divide it into cells. How many people have incomes in this range? How many people have incomes in this range? How many people, for these disjoint ranges, right? So we can have an arbitrary collection of cells. K could be as large or as small as we want, but the sensitivity of this query is still just 1. That is, the presence or absence of one person can only change the count in one cell and can only make that, in that cell, it can only change the count by 1. So the L1 sensitivity is 1. So this was kind of the first indication that we had something very powerful. Okay. Now, I want to just tell you about one technique, which will show up again later, but it comes back to thinking about sampling. So I said that the sampling intuition was good and was on the right track, but it needs some help. So here's a way in which sampling helps with differential privacy. Given an epsilon, suppose we have in our hands an epsilon differentially private algorithm A that just maps data sets to some space of outcomes. And we're going to modify this as follows. Well, we're going to have a new algorithm where for every element in the database X, so X is X1, X2 up to Xn, for every element, we're going to flip a coin that comes up heads with probability alpha. If it's heads, we retain Xi, and if it's tails, we throw it out. So this gives us a smaller database of size approximately alpha times n, and let's call that database Z. And now we run our algorithm A on this smaller set, this subsample Z. Then theorem says that the resulting algorithm is, well, this funny looking bound. This is basically, when epsilon is small, this is essentially 2 alpha epsilon, or is bounded by 2 alpha epsilon. So the resulting algorithm is alpha times e to the epsilon minus 1 differentially private. And the intuition for why this is true is that an individual only actually suffers a privacy loss in this execution if their data are retained. If the data are thrown out, then of course nothing is going to be leaked about them. So that intuition isn't a proof, and there's more to the proof, but the intuition is a good guideline. And very importantly, though, this relies on the secrecy of the sample. If you start reporting whether or not you're in the sample, then privacy gets destroyed. Okay? And that gets back to what we were talking about at the very beginning. Nobody knows I was in the sample. You know, I could have claimed I opted out. So here we see that coming back for us. Yeah. Another notion that we're going to need is approximate differential privacy. And this is just a small relaxation of the original definition. Now we have a second parameter, little delta, that shows up here in red. And it's the same definition as before. Everything in blue and black is what you saw before, but we now have this additive plus delta term. So let's see, that relaxation turned out to be very useful. So why? Well, one thing is it actually lets us use Gaussian and binomial noise. So Gaussian, if you look at the tails, if you look at draws from the Gaussian distribution that are out toward the tails, they will not satisfy the bounded ratio condition that I gave. Of course, you're unlikely to be far out on the tails, so that escape hatch is given by delta. Another advantage, and an advantage of Gaussian noise is that instead of defining the sensitivity, so we have almost the same algorithm, but we're now adding Gaussian noise whose standard deviation looks something like delta epsilon over f, just like the parameter was before. And but we get to use L2 sensitivity for delta instead of L1 sensitivity. So when we're looking at many counting queries, for example, this lets us improve by a factor of square root of k. Also, privacy loss is a random variable. The bound epsilon is an upper bound on privacy loss, and usually things aren't as bad as that. In fact, usually the privacy loss looks more like epsilon squared. So when epsilon is less than 1, that's a huge advantage. So this gave rise to the so-called advanced composition theorem, which says that if you look at the composition of many differentially private algorithms, k of them, then the privacy loss, instead of being k epsilon, is actually closer to square root of k times epsilon. That is, with probability at least 1 minus delta, the privacy loss will be bounded by square root of k log 1 over delta for any delta. And that gave rise to a whole slew of stronger definitions of different concentrated differential privacy and its cousins, zero mean concentrated differential privacy, Rényi differential privacy, where basically the privacy loss random variables are sub-Gaussian, and you can get better bounds. And I believe that the Census Bureau will be using the ZCDP of Bunn-Steinke. So delta also is, as I said, a general escape hatch. It lets us, for example, use cryptography to simulate a trusted center. So delta will capture the probability that the adversary breaks the crypto system. It also lets us make some nice connections to the field of robust statistics. So robust statistics is a subfield of statistics that tries to cope with small amounts of measurement error and, in old terminology, a few wild data entry errors. So just some complete craziness. And the results in that field are not worst case. They're sort of distributional with a single worst case perturbation. So the assumption there is that the data come from sort of nice distributions where the definition of nice depends on what it is you're trying to do. And what we can do in differential privacy is we can privately test to see whether the data look as if they come from a nice distribution. And if not, you can just quit and say, I'm not answering this because I can't do it privately. And this was done in a differentially private way, so you haven't harmed anything. Or if everything seems nice, you can go ahead and use these nice, robust estimators, which sort of cope with a few outliers nicely. You might, however, because your test is differentially private, you might think you're in a nice situation, but in fact, the data really aren't nice. And you just need to be sure that your probability of making such a mistake is small, and that's again captured by a delta. Also, you can get rid of the dependence on the number of cells of the L infinity error for histograms. We saw a log of K over something, and that will go away. All right. So there are a lot of good reasons to relax. And now we can get to where we first defined that relaxation, and we leave the centralized setting. So this was the first paper on distributed differential privacy. It's in your standard distributed setting, and you have these different parties, and they don't trust each other. However, so the trust boundaries are just around each individual. They don't trust anybody else. But maybe they're going to trust cryptography, so these edges have some trust associated with them. And as usual, when you're handling Byzantine faults, you're sort of trusting that there's a strong majority of good players. So those are trust assumptions for this. So the idea was to literally put differential privacy into the distributed setting. Here's a straw man for sums. You could share out your value using verifiable secret sharing. Letting sigma squared be the variance you need for whatever your epsilon differential privacy is for this sum. You can share out xi plus a draw of sort of 3/2 sigma squared divided by n. Why 3/2? Because you're assuming that 2/3 of the players are playing correctly. So you're going to get at least n times 2/3 or sigma squared when you add everything up. You can sum out the shares and reconstruct, and you'll end up with the sum of the xi's and some normal noise. And tau squared will be, good. But with this kind of an algorithm, the Byzantine player can completely destroy things by sharing out for their noise some wildly huge value. And that'll just completely trounce any real signal here. So we look at a more modular approach where we share out the inputs and we verify their legitimacy. So for example, and we did this, suppose we're doing a counting query. So each person applies to their data a counting query and then shares out a bit, 0 or 1. So what should be shared out will be a 0 or 1. So we share these out, we verify legitimacy using secure multi-party computation. We then compute the shares of our function, in this case the sum, and we then engage in a Byzantine fault tolerant distributed noise generation protocol to share out a noise value. And then we add the shares of the noise and the shares of the function, and we reconstruct. So this has been done for counting queries. And this work had a few properties. So first of all, this was a very self-determination work. So the idea was that each individual would manage her own privacy and her own data, and she would have a cumulative privacy loss that she was willing to endure. And when requests for the use of her data would come along, she would decide whether she wanted to spend her privacy budget on these. So she might love to do medical research and allow her data to be used for medical research, but she might not want, want to participate in certain kinds of things. And I was inspired later by, I heard a talk at a workshop. The talk was by Hank Greeley, who is a professor of law and by courtesy also of genetics at Stanford. And he said, and I wish I had written it down, so this is not an exact quote, but he said, I don't want my Irish blood being used by the English for a study on alcoholism among the Irish. So people have strong feelings about what kinds of questions they want to let their data be used for. And the goal in this, the dream in this work was to try to enable this self-determination. Okay. On the technical side, we gave efficient multi-party communication, secure multi-party communication protocols, computation protocols for fault-tolerant distributed noise generation. So we had a method for binomial noise to approximate the Gaussians and Poisson noise to approximate Laplace, and methods that were efficient for generating shares of many unbiased bits and constructions of circuits for flipping many independent coins with common bias, which was needed for the Poisson noise. Okay. Now, another model, which actually dates back to a protocol of Warner in 1965 for enabling people to answer surveys about embarrassing or even illegal activities, is formalized as follows. We have our users, and each user has data, X1, X2, and so on. And then the user applies some randomization operation. So X1 gets mapped to R of X1, X2 to R of X2, and so on. And that yields some messages. Well, those are called messages. And these messages are then sent to the data analyzer, who again, like our analyst, might not be trustworthy or nice or whatever. And notice that the trust boundary here is around the user and the randomization of the user's data. So the trust boundary does not extend around the yi's. And okay. So here, noise is introduced by each user, and that noise adds up in the yi's, and that leads to a large error and large sample complexity. But I'll give you an example of how this works. So this is the classical randomized response protocol due to Warner. Flip a coin with probability P of heads. In Warner's example, P is equal to 1/2. So you could use a real coin to implement it. If heads, you're going to answer randomly. And if tails, you're going to answer honestly. Okay? So the privacy analysis is straightforward. The privacy that you say yes, I floss regularly, given that the truth is yes, is 1, divided by the probability that I say yes, given that the truth is no, is this expression. So if the truth is yes, you'll say yes if the first coin is tails, which has probability 1 minus P, or the first coin is heads and the second coin is heads, which is, should have written 1/2 there. P over 2, not P squared over 2. So that's 1 minus P plus P over 2. So that's the numerator for this. And then if the truth is no, you'll say yes only if both coins are heads, which has probability P over 2. Okay, so good. And then you choose P so that this value is less than or equal to epsilon. Given this, you can reverse engineer the noise to learn the approximate flossing fraction. So the number of true yeses among the approximately 1 minus p times n that answer honestly is the number of yeses that you observe minus, how many yeses came from randomness, which is p times n over 2. Okay. So that gives you the fraction. Okay. And for constant epsilon, the error that you get here looks like square root of n. And compare that to in the centralized model where you have noise that looks like 1. Okay. But despite this, the local privacy model is very popular in industry. And the reason is that the trust barrier was moved to the client. And that means that you reduce the liability at the server. So here are some uses. Google has the Wrapup project, which handles hundreds of data analytics metrics. Microsoft uses it in Windows telemetry for user experiences and for machine learning of predictive models. Apple uses it for learning new words that are becoming popular, emojis, deep links, lookup hints inside notes, health type usage, Safari, and so on and so forth. There's also some connection to private federated learning, and I'll say a little bit more about that later. And again, the price is that it's less accurate. And there's another issue, by the way, for industry use, which you should keep in mind. They measure and they measure and they measure and they measure the same things day after day after day, and many, many, many things. So there's a huge amount of composition. And some systems have tried to address this. There's the Wrapup, which was actually used in practice. And then there's some connection to what we call privacy under continual observation, which was first worked out in the central model and then adapted to the shuffle model. I shouldn't have said central here. I should have said streaming with a centralized curator. Okay, and now we come to something that's quite new. So this was a 2017 paper, which is very, very thoughtful and extremely thought-provoking. And it tries to lay out a complete architecture for privacy, for analytics in a crowd. And this architecture included, for example, an efficient, scalable, oblivious shuffling algorithm based on Intel's SGX, or software general extensions. So this is hardware-based encryption that isolates specific application code and data in memory. And an interesting thing about this paper, aside from its intellectual content, is that it appeared in SOSP. So it was a systems paper. And it was trying to reach real practitioners. So as a result of this, people formulated what's called the shuffle model. I mean, they were talking about shuffle in the Proclo paper, and here's a formalization. And here's what it looks like. It starts off like randomized response. We have X1, we apply the randomizer, and this produces messages, maybe multiple messages per person. In some protocols, there are reasons to give multiple messages. Then the messages are fed to a shuffler, and the shuffler is, one of the trust assumptions is that the shuffler is good and it does a truly random permutation of all of the messages that it receives. So in this case, it's receiving 2n messages and it completely randomly permutes them. And that's the trust boundary. What is output are these shuffled messages. So the same things that came in, but permuted randomly. And that collection of shuffled messages is handed to the analyzer. So the randomizer has to be designed so that this whole box satisfies differential privacy. It may not be that Y1 and the Y1 messages are differentially private, but the combination must satisfy differential privacy. So, Why is this interesting? Remember that the price in the local model is less accuracy, and there's also huge amounts of composition. So there's a theorem that says for small enough epsilon and any delta, if the local randomizer, that little box that the user uses, is epsilon differentially private, then the shuffled algorithm will give this kind of differential privacy in the central model. So what is this kind? It's that same epsilon, and now we're multiplying it by log 1 over delta, square root of log 1 over delta divided by n. So if n, the number of users, is very large, which it is in many of the internet settings, even if you're sort of breaking it into small, anyway, in internet settings, this is huge. This is amazing. So what this says is, if they actually, so when you give your data sometimes on the web, you're told your data are aggregated, and your data are anonymized and aggregated. So if the anonymization is real, like, and your multiple messages cannot be linked to one another, so they're really anonymized and really unlinked, and then whoever observes these things only observes the aggregation, like the outcome of the computation, this will substantially mitigate the cumulative privacy loss. Now, another corollary is this transformation also yields a sort of noise floor for randomized response in the central model. If you're going to have privacy that has a square root of n in the denominator, that says there has to be a lot of noise. Okay. All right. So this was pretty exciting, and there's been a lot of work. So I'm just mentioning a couple of results. Subsequent work by Feldman, McMillan, and Talwar gets asymptotically optimal dependence on epsilon, even when epsilon is large, not less than a half, no bound on epsilon. And also, I didn't discuss it, but there are some variants on exactly how the randomizers can work and whether information can get passed from one party to another before it applies its randomization. And it seems all really weird and so on, until you try to think about using this in the context of something like stochastic gradient descent, where in the actual randomness that's used to perturb and update step depends on where you are right now in the gradient descent algorithm. And then you see you need different randomizers for different people as the application, the execution advances. So this is a really nice illustration of that. And they get asymptotically optimal privacy analysis for noisy stochastic gradient descent when you sample your points for the gradient descent without replacement. Okay, so I'm going to tell you about one concrete protocol and its analysis in this model. This is Chu et al. So remember the randomized response algorithm. Now in the shuffle model, assuming that P and that N is large enough and so on, we're going to run randomized response with this value for P. So this is, order 1 over N times this funny thing squared log of 1 over delta. Now, the way to think about this is when you do that first flip to decide whether you're going to answer randomly or not, you're creating a small set of users who are not going to report their data and who collectively are going to report some random bits. Everybody in that set is going to flip. So this is randomly selecting a subset of users who, instead of contributing their values xi to the sum, will draw from an appropriately scaled binomial distribution. And if you look at this, it turns out that the variance of this group binomial will look like log of 1 over delta divided by epsilon squared, which is exactly the notion, the amounts that we were talking about earlier. So this is correct. So here's the analysis. First, you choose from that first flip a set H of individuals who will answer randomly. And you analyze for any fixed and sufficiently large H, the privacy loss. And from the analysis of the binomial noise that we did back in our data ourselves work, we see that we get a privacy guarantee of log 1 over delta divided by the size of H. So this is where we need H to be sufficiently large. Then we apply the randomness of the subsample technique that I mentioned earlier for sort of understanding the privacy for everybody, because there's only a 1 minus the size of H over N probability that you're going to be actually contributing your data. So we get to multiply by this 1 minus the size of H over N. And finally, we argue that H is with this value of P, H is very likely to be close to its expectation, and that's from a Chernoff bound. Okay. So that's, in a nutshell, what their analysis is. And the accuracy that they get is asymptotically correct. It's 1 over epsilon times the square root of log of 1 over delta. So in this setting, for this particular problem, if you have a shuffler, you don't pay the price for local differential privacy. But you need to trust the shuffler. Okay. And this protocol is incredibly succinct. The user only sends 1 message bit. Okay. All right. Now, federated learning, and I'm about to wrap up. So federated learning, I thought I would talk about this today, but I decided it's a little hard for me. I had a little trouble understanding exactly what people mean by federated learning. So intuitively, don't think so much about individuals now, but maybe hospitals who are not permitted to share their data with one another, but they want to train models on the union of their data. And it's not clear what are the privacy requirements of federated learning. I believe that in many cases, federated learning might be done without enforcing any formal notion of privacy. But you can look at privacy preserving federated learning. So maybe viewed the right way, this would be some kind of combination of secure multi-party computation and differential privacy. So with that in mind, let me just wrap up now. There are many technical open questions in the shuffle model. So to it all, I didn't mention it, but they consider it a form of robustness, a failure to participate. And it's known that this can hurt multi-round protocols in the shuffle model, but it's not known whether this refusal to participate can hurt single round protocols or single message protocols even. More fundamentally, what would it take really to get this model deployed? Clearly, Google is not going to do a random permutation of all of the messages that it gets. Things are going to be done in batches. Crowds are going to be defined one way or another. So what would it take to make this shuffle model a reality? What's the right setting for it? Okay, there's some very beautiful work on the structure of local differential privacy. So for example, Bunn, Nelson, and Stemmer showed that, I didn't talk here about group privacy, but if an algorithm is epsilon differentially private in the central model, then it's automatically k epsilon differentially private for a group of k. So if you have a family of size 5, it's 5 epsilon differentially private for your family. Group privacy, they show, is more like square root of k epsilon instead of k times epsilon that we would have in the central model. That's very exciting. Try to delineate the federated learning from something called secure aggregation, which roughly speaking is modular arithmetic on user messages, versus the shuffle model. Yeah, and see sort of structurally, are there real differences? Look at multiple rounds in the shuffle model and other fault models. So there is some work that looks at honest but curious with and without honest majorities. That's kind of more in the lines of what's typically done at PODC. And finally, this self-determination that we envisioned in our data ourselves has not been realized, but I don't see why it can't be. So find a way to make this real. Okay, thank you.